Ali,
Meeting
Aaron
is being recorded.
and Joshua Sussin, who Josh is also in the audience today. Okay, yeah, so to start off, let me first tell you guys what my current research mission is. So my current mission is to develop and understand the mathematics of topological quantum computation from the perspective of the modified trace theory. So this mission of mine can be broken up into two overarching research agendas. The first agenda is how can modified traces extend our understanding of the mathematics of topological quantum computation from the semi-simple to the non-semi-simple setting. So this will be the focus of today's talk. Second, another agenda that I'm curious about is how can modified traces refine our existing mathematical understanding of these semi-simple models? So if you're a visual learner, a visual summary of what I'm trying to achieve is that I like to combine these two textbooks here. So on the left is the textbook by Zhonghan Wang that introduces the mathematics of topological quantum computation. And on the right is this new and upcoming textbook by Nathan Gear and Bertrand Petromaran that introduces this theory of modified traces to study non-semi-simple quantum topology. So what I'd like to do today is tell you guys about this new initiative we're doing called non-semi-simple topological quantum computation. And I'll do that by telling you guys the mathematics behind what we call the non-semi-simple Ising anyon model. And of course, throughout this talk, if you have any questions, please stop and ask me any questions. I can see the chat here, but if the organizers can see the chat, then please echo them out to me. So let's just kind of first review what topological quantum computation is. So you can think of a topological quantum computer as a type of quantum computer whose platform utilizes topological phases of matter and who has this interesting property that can create point-like excitations called non-abelian anyons. So we would like to use these non-abelian anyons to perform quantum information processing. So I like to start off my talks with this slide here because I think it does a great job of explaining at the rudimentary level how language across these different disciplines can be translated with one another. So if you are a mathematician, maybe working in quantum topology, you would look at this diagram and you would immediately think about the Hopf link here. And one way you could view this diagram is as a ribbon graph, and you can break it up into these fundamental pieces involving the co-evaluation. So the co-evaluation is a map from the monoidal unit to V tensor V dual. So we apply co-evaluation here, another co-evaluation here. And then we can study braid group representations on these objects to braid them around, and then we'll apply evaluation back into the monoidal unit. Now, if you are a condensed matter physicist, then you might look at this diagram and tell a different story. So the story goes, you start with a two-dimensional system at the vacuum state. You create two pairs of anyons. Then you move them around the surface. So in the space-time graph, they will create these braiding trajectories. And then you will fuse these anyons back into the vacuum state. Now, in the quantum information processing point of view, you would view this first portion as a way to initialize your quantum states. Moving these anyons around the surface will correspond to applying our unitary transformations in our system. And then fusing the anyons back is part of the process of measuring our output, the information that we processed. So furthering along this language exchange, so in the context of topological quantum computation, when someone says that they have a unitary modular tensor category, I immediately think of it as a data structure that encodes the algebraic theory of anyons. So a feature of these unitary modular tensor categories is that there are isomorphism classes of simple objects, and each isomorphism class corresponds to a type of anyon that can exist in your model. And in particular, one of the simple objects is reserved for the monoidal unit in our category. This will correspond to the vacuum state. Our category has a direct sum and tensor product. This will correspond to quantum superposition and the fusion of anyons respectively. And we also have a family of braiding isomorphisms, and this will correspond to the data of braiding of anyons. Okay, so how about we just jump right into a concrete example? So consider the Ising modular fusion category. So to the experts, this is related to the SU2 level 2 transaminase theory. You get this category by considering some category representations over quantum SL2 at the eighth root unity. And then you semi-simplify, and what you're left with is this rank 3 modular fusion category. So rank 3 means that the number of isomorphism classes simple objects is precisely 3. So 1 is, of course, reserved for the vacuum. And then the other two anyon types is the Ising anyon and the fermion. So in the representation theory literature, we like to enumerate our objects by our highest weights. So we enumerate them usually by S0, S1, S2. But in the anyon language, we will prescribe the notations of 1, sigma, and psi to denote the vacuum, Ising anyon, and fermion. So once we've specified the anyon types that can exist in our model, the next question one might ask is, what are the fusion rules? So here, let's examine the one in the middle. So in the representation theoretic language, we would say that, oh, S1 tensor S1 is isomorphic to S0 direct sum S2. S0 direct sum S2. In the anyonic language, you would say when you fuse two Ising anyons, you will either output the vacuum or the fermion. And so once I've specified my fusion rules, then I can know what are the admissible trivalent morphisms. So in the representation theory context, this trivalent graph will correspond to the map that embeds S0 into S1 tensor S1. And this trivalent graph will correspond to the embedding of S2 going to S1 tensor S1. But this will represent the fusion of two Ising anyons and then their outputs respectively. One thing that I like to emphasize is that when we draw these pictures, they are actually matrices in disguise. So the way you actually compute these matrices is kind of like playing a game of Sudoku. So there are a set of rules and constraints, and you play the game, and then you can actually fill out these entries to compute this matrix. So whenever I draw this trivalent picture here, up to a scalar, it is equal to this matrix. So you compute this by looking at the quantum group relations. So in particular, in this example here, we have to send the highest weight to this highest weight. So we will have 1, 0, 0, and we apply the delta Fs to get the rest of the entries of this matrix. So every time I draw this picture, it is secretly a matrix in disguise. And using these trivalent graphs, we can build out bigger and bigger fusion trees. So here is a fusion tree. And you do this by taking the Kronecker product and the composition. So this tensor product will correspond to horizontal juxtaposition. So I draw these pictures side by side. And the composition will correspond to vertical stacking. So here, observe that if I put this picture right underneath these guys here, then I'll get this picture here. But once again, this picture here is a matrix in disguise. You get this matrix by taking the Kronecker product of whatever this matrix is with the identity matrix, and then you multiply by whatever this matrix here is here. Okay, so
Some question here.
yes.
So why is a 3 by 4 matrix? So 2 is not a simple object, some projective.
So here 2 will correspond to S2. This has quantum dimension 0, and this is a three-dimensional representation. So S0 is our monoidal unit, which is one-dimensional. S1 is our two-dimensional, and S2 is three-dimensional. And so here, S1 tensor S1 will be a four-dimensional guy. So we have 4 rows here, and S2 is three-dimensional, so there are 3 columns.
So this is not a topological space at all. This is just the representation thing.
This is just a representation map
Okay.
from
Okay.
S2 going to S1 tensor S1.
Okay. Okay. Thanks.
Mhm. Yeah, so today we're here to talk about topological quantum computation. So I'll talk about the qubits. So the place where we encode our qubits are in these Hom spaces. So as an example, if we look at the Hom space from S1 going to S1 tensor S1 tensor S1, so three guys, this is a two-dimensional Hom space. It is semi-simple, so I can write down these fusion trees as my basis for this Hom space. So here I wrote down the left-hanging basis, and I'll label one of the basis elements as the 0 and the other one as 1. Now, no one is stopping me from writing out the right-hanging fusion tree basis, and this is a completely valid choice of basis for this hum space. And so what the category provides is what we call the F symbols. So these are the change of basis data that goes from the left-hanging to the right-hanging. And in particular, these F symbols satisfy certain axioms called the pentagon axioms that allows it to be consistent throughout. So the next set of data is what we call the R symbols. So if C is a simple object or an anyon type, and here I'm just going to assume multiplicity free, then this matrix here that corresponds to C going to A tensor B and then braiding it is equal to the matrix that corresponds to C going to B tensor A up to some scalar, and that scalar is what we call the R symbol. And so once I've specified my anyon types, what my fusion rules are, the F symbols and R symbols, then I can start writing down what my braid group action is. And so here, B1, which is the one where I braid the first two strands, this will have this diagonal matrix here. The reason why the matrix is diagonal is because if we were to braid the first two strands, then it is exactly in the setting where I can collect the R symbols. And so for sigma 1, for B1, we just collect the R symbols and we get a diagonal matrix. Now for the braiding the right two strands, this requires a little bit more work. So here, if I were to braid the first two strands, the last two strands, then it's not really in the setting yet to collect the R symbols. So what I do first is I apply an F move to go from this basis to this basis here. I braid it to collect the R symbol, and then I apply an inverse F move back into my original basis. So here to compute B2, you apply F, collect the R, and then apply the inverse F, and you will get this matrix here. Okay, so the reason why the Ising anyons are famous in the literature is because they are often cited as the most promising candidate for physical realization. And so here is a graph depicting the fractional quantum Hall effect. I won't go into the details of what this graph means, but in particular, it is theorized that at the nu equals 5 half fractional quantum Hall state, so at this plateau is where we conjecture to experimentally see the Ising anyons. Another notable place is this 12 fifths. This is where we conjecturally expect to see the Fibonacci anyons in the Fibonacci modular fusion category. So despite the fact that these Ising anyons are the most promising candidates for physical realization, they have one downside. So before I go into the downside, let's recall the following definition. So a finite set of quantum gates is said to be universal for quantum computation if any unitary operation can be approximated up to arbitrary accuracy. So in the context of topological quantum computation, our finite set of quantum gates is precisely the generators of our braid group. Now, in the context of the Ising modular fusion category, it is not universal for quantum computation by just braiding alone. Now, some quick comments. First is that this Ising modular fusion category can only generate the Clifford gates by just braiding the Ising anyons. And there are non-protected operators, such as the magic state distillation, that you could use to achieve universal quantum computation. But idealistically, we hope that all the operations that we perform are all protected topologically. And so the question of the day is there any way we can make these Ising anyons universal by just braiding alone? So let's take a step back and think about what the subject of braiding anyons really is about. So I think of this subject as this interaction between modular tensor categories, TQFTs, and topological phases of matter, and the collection of these subjects we're trying to study quantum information theory. Now, this subject was developed in the late 90s, early 2000s by a series of works by Friedman, Kataev, Larson, and Wang. And at the time, the mathematics that were readily accessible at the time were precisely these TQFTs that were constructed from semi-simple modular tensor categories. So most of the literature that you see on the archive and etc. Are really focused on these TQFTs that are constructed from semi-simple categories. But now, in more recent years, we have a much better understanding of non-semi-simple TQFTs. And so we have this entirely new landscape to study the subject of topological quantum computation. And so this brings us to this idea of non-semi-simple topological quantum computation. So really the idea is that we would like to bring some of the new mathematical instruments that appear in non-semi-simple quantum topology to the mathematics of topological quantum computation as a means to better understand this field overall. Are there any questions before I move on to discussing what the modified traces are?
So I guess maybe a quick comment is that I guess in your previous slide, the correspondence is for 2 plus 1 dimensions.
Yes,
There's
yes,
module tensor categories.
yes, two
Oh
plus
yeah,
one.
okay, sorry, you have
Hmm.
okay,
And then here I'm only going to be talking about surgery TQFTs.
okay.
Okay.
Okay, I
So,
do have one more question about the home space. So
mhm.
the 3 by 4 matrix, that's just linear algebra, but there's a home space, which is the intertwiners. What's the dimension of that space?
The intertwiner, the braiding on
Yeah,
S1,
yeah,
S1,
well, yeah. Well, no,
this
the
will
home space.
be,
It's just the intertwiner space from 2 to 1 tensor 1. Is that just like a 3 dimension, 4 dimension or something?
it should be one-dimensional.
No, I think it's
Wait, sorry, could you repeat the question?
so the 3 by 4 matrix, that's nothing but the 2 is a 3 dimensional representation, 1
Hmm.
tensor 1 is a 4 dimensional representation. So you have
Hmm.
a 12 dimension just because the matrices. But there's a Helm space. The Helm space should be the intertwiners because they are representation of something. So I want to know the dimension of the representation intertwiner space. I believe that's either 3 or 4.
Jayhan, I'm still not understanding completely. Because if we tensor S1 and S1, doesn't that decompose as a single S2 and an S0?
Mm-hmm.
But then S2 is probably a Stanford, right? It's both it's not simple. Oh, it's a simple.
It is
It's
simple.
simple here,
Yeah,
yeah.
it is
So
simple.
so for this one, it's just Schur's lemma, and you just have a one-dimensional
Then
space.
I'm
Yeah.
confused. So okay,
Yeah.
you're right. This is the simple setup. I'm thinking the non-semi-simple.
Yeah,
Okay,
so here everything I mentioned so far is in the context of semi-simple case and multiplicity free. So C is a simple object, A tensor B is multiplicity free, so Schur's lemma will just tell us that it's
okay,
some
okay.
scalar.
Sorry, I was thinking the wrong thing. I was thinking the intertwiner.
Yeah, if
Okay,
it's
it's one
S3, then you'll
dimensional.
get some more weird stuff.
For
Okay,
sure,
okay.
yes.
Yeah, and then actually the matrix given by Sung in that slide is probably, I mean, that's an intertwiner, right? It was intertwiner, yeah, that one, that matrix. I guess it represents the intertwiner morphism from S2 to S1 times S01.
Okay, that could be the okay. Anyway, I misunderstood the
That is
thing.
a representative of the one-dimensional space. It's the either the projection or the inclusion of S2 into S1 tensor S1.
Okay,
Yeah.
okay, okay. I think I got it. So then this is the topological part of the thing. Okay.
Cool. So next I'd like to talk about the modified traces. So I want to first just iron out the terminology.
Uh,
So,
is there any question? Sorry,
or was it an echo from my part?
no, there seems to be some background voice. Uh,
Okay, I will continue.
uh,
So when
okay,
I
sorry.
say modular tensor category, what I mean is a non-degenerate ribbon category that you could use to construct a surgery 2 plus 1 TQFT. And when I say a modular fusion category, I really mean a modular tensor category that is semi-simple and has finitely many isomorphism classes of simple objects. And you could use this modular fusion category to construct the Witten-Rechtstreich of 2 plus 1 TQFT. Now, today's talk will be about this new categorical structure called the relative modular category. So this permits non-semi-simplicity and infinitely many isomorphism classes. And you could use this category to construct what is known as the Blanchet-Constantino-Gear-Petro-Moran 2 plus 1 TQFT. And so the reason why I mentioned this is because if you look at the literature, and most papers in the 2000s and the 2010s, they will say modular tensor category, but really, if you read the context, they are focused on the semi-simple and then the finite case. So for the purpose of this talk, whenever I say fusion category, I really mean a tensor category that is semi-simple and finite. Now, in order to relate these categorical structures to topological phases of matter, we need some notion of unitarity. So in the semi-simple finite setting, the unitary structure is attributed to the works of Krylov and Hans Wenzel, and we call these categorical structures unitary modular fusion categories. In the relative setting, the unitary structure was constructed by Gear, Lauda, Petro-Moran, and Josh Sussin, and we call these categories relative Hermitian modular categories. And I mention this because if you're interested in learning more about this subject, then this is precisely the keyword that you should be looking up.
Question
Okay,
here.
so
Yeah,
when I
Sam.
first learned this subject, it was not obvious at all how you can get from a category
Question,
to
son.
a TQFT. So the
Son,
way
I
you
think there's a
actually
question.
get a category to a TQFT, you have to hit
Sam, can you hear me?
milestones. So
Son,
what you do is you take a modular
There's a
tensor category.
question.
Yeah, but somehow the microphone is not working.
okay,
Oh, is my
I can hear
microphone not
you.
working?
No,
I can hear
some.
you.
Yeah, we can hear you, but there was a question, I believe.
Oh,
Yeah,
sorry.
yes. I have a question. Can you hear me?
Yes, sorry.
So can you go back to the unitary thing? So this unit, I don't know this reference. So the unitary structure, is that really make this whole thing unitary, or it's just pseudo-unitary or some other meaning of unitary?
So my understanding is that given a modular fusion category, you could give it a definite unitary structure, but people have been classifying pseudo-unitary structures on modular fusion categories
No,
as
no,
well.
no, no. I'm talking about the next line, the relative modular
Oh, the
category.
relative setting.
It's
That's
a
pseudo
truly
unit.
unit. The other one I believe is truly
Yes,
unitary. So
so
it's the second one.
the examples that we will be focused on today will be pseudo-unitary as the
Okay.
TQFT as a whole.
Okay. That's the main thing because I think, well, I just since I stopped you, I might as well say. So I'm definitely very interested in make this whole modified trace unitary.
Yeah.
That's
Okay.
not hard at all. You just pick a orthonormal basis. The question is how big is the symmetry?
Question,
So
Zheng though, is if you just took a basis where it was orthonormal, it wouldn't be compatible with tensor products, I think.
yeah,
So
that's the issue. That's
right.
so the issue is either it's a compatible, monoidal everything with this thing.
Right.
And obviously, this will be a symmetry breaking setup. My question is, does anybody know this will completely, break the symmetry to nothing? There's nothing left.
Hey, I'm maybe I'll have to think a little more, but I'm almost positive that with these non-semi-simple ones, you'll have to be pseudo-unitary at best. Not You'll never be actual unitary
Yeah,
on the whole category.
especially because the quantum dimensions will have negative modified quantum dimensions in some simple objects.
Well, I don't think the quantum dimensions really matters. So,
Don't they say that you need positive quantum dimensions in order to have a unitary structure that is not pseudo-unitary?
no, I think the way I would say it is the quantum dimension doesn't matter, zero or not. So the Hilbert space structure you want is on the Helm space. So the vacuum, it doesn't really matter. It's just a reference point. So quantum dimension 0 or anything, it doesn't really matter. What matters is the process on the vacuum. So the question is, if there's a good inner product which is unitary, has a large symmetry. Anyway, I think we should go on, but I'm just saying there's a lot of things here we don't know, but I just want to confirm this is not a true unitary in the sense of quantum mechanics.
Yes. Yeah, so let me mention this construction from the category to the TQFT. So there are certain milestones that you like to hit in order to actually construct the TQFT. So you take the modular tensor category, then you want to construct an invariant of ribbon graphs or the framed knots and links. Once you've constructed the invariants of framed knots and links, then if they are invariant under the Kirby moves, then you can construct an invariant of decorated nice three manifolds. And once you've constructed the invariant of three manifolds, then you can start to think about what the state spaces are assigned to and construct the TQFT. And so in the semi-simple setting, there are mathematical instruments that we use to go from one milestone to the other. So in particular, we use the categorical trace to construct this invariant of links. There is a notion of a Kirby color to have our invariant of links invariant under the Kirby moves to construct a three manifold, and there's a universal construction to construct the TQFT functor. Now, in the non-semi-simple setting, we have new mathematical instruments. So the categorical trace is replaced with the modified trace. The Kirby color can be replaced with a notion called the chromatic maps, and there is a generalized version of the universal construction. Now, I like to tell you guys about this modified trace, but in order to really appreciate the role of the modified trace, we need to first just briefly review how the categorical trace appears in this construction of knots and the three manifolds. So I'll quickly review this in the graphical calculus language. So let F be an endomorphism on V. So we'll define the trace as just the Markov closure of this morphism. And the quantum dimension on V is defined as the trace of the identity on V. So it will just be a single loop. So if V is absolutely simple, meaning that the endomorphism on V is just every endomorphism on V is some scalar times the identity, then I can write every endomorphism of V as this Langle F wrangle V. So this will denote the scalar of whatever this morphism is. And so when I take the trace, what I'll get is that scalar with the quantum dimension on that object. So the way you construct the invariance of knots and links is you view the knot or link as the Markov closure of some braid word. You color it by an object in our category, and now this is a morphism from the Monod unit to the Monod unit, and you can extract the scalar. So this is how you construct the invariance of knots, of framed knots. And to construct the three manifold, we have this notion of a Kirby color. And so we color this knot by a formal linear combination of our simple objects where the coefficients are given by the quantum dimension of that symbol. So observe that if the quantum dimension of our object is 0, then it doesn't contribute to the three manifold invariant, and therefore it doesn't contribute to the data of the TQFT. And in fact, if the quantum dimension of V is 0, then we can't even build any knot invariants out of it. So it was really critical in the semi-simple setting to only work with objects with non-vanishing quantum dimensions. And so if you naively take some category representations over, let's say, quantum SL2, then this is a non-semi-simple category. There will be these projective objects, and that has this feature that where no matter what knot or link you color it by this projective object, it will evaluate to 0 under the endomorphism of 1. And so what we did in the semi-simple story is that we performed something called the semi-simplification procedure. So long story short, what we did was we threw away all these projective objects. And so what we like to do in the non-semi-simple setting is avoid the semi-simplification procedure and try to keep as many of these objects that have quantum dimension zero. So in particular, today we'll focus on these projective objects. So the way we actually construct the link invariant, the framed non-invariant that involves the projectives is by cutting along one of the strands that's colored by this projective. So here I have a pair of scissors and then I'm gonna cut along the strand. Okay, so I hope no one blinked on that part. Let me just redo that. So I'm gonna get a pair of scissors, I'm gonna cut it, and then I didn't animate the rest, but now you're gonna open this up and hopefully people can visualize the trefoil with one of the strands open. And this is the picture that you get here. And so the way the modified trace works in this context is that rather than taking the full Markov closure, we will take a partial trace. So here, as an example, there are two strands. Rather than closing both V and W, we will just enclose one of the strands, in this case W, and we will leave V, which is colored by the projective, open. So the modified trace is defined as this modified dimension, which is just some scalar that satisfies some consistency equations times the scalar that corresponds to the partial trace, where we assume that V is a simple. And so as an example, the modified trace on the trefoil will be that modified dimension of that object that we're cutting the strand along by, times the scalar that is proportional to the identity. So this is the modified trace of the trefoil. And so one thing that I'll mention is that this strategy of cutting along one of the strands, this dates back to 1992 in the construction of the ADO invariants. So in particular, these modified traces, in the case of quantum SO2, they recovered the colored Alexander invariants. Okay, so the next thing I'd like to discuss is this categorical structure known as the relative modular category. But are there any questions about the modified traces?
What is the biggest ideal you could choose so that the modified trace is non-zero on the objects that you care about? Is it the
So,
projective ideal?
so in the context that I'll talk about today, which is the category coming from the unrolled quantum SL2, I believe that the projective ideal is the only ideal that you can consider to have a non-degenerate modified trace.
All right, thank you.
But I'm sure there could be some exotic examples out there where there are maybe the modified trace isn't unique, but I'm not aware of any examples at the moment. Okay, so let's talk about these relative modular categories. So here, the relative modular categories provide you this non-semi-simple 2 plus 1 TQFT. So when someone says that they have a relative modular category, structurally, this means that it is a linear ribbon category. And this category also has something called an M trace. So this M trace should be viewed as a family of K-linear maps that go from the endomorphism of V to the ground field, where V is an object of some ideal of the category. And another important part of this category is this relative data. So this consists of G, X, and Z, which I'll now explain. So G is going to be a commutative group, and this will essentially tell us the grading of our category. So this X is a small symmetric subset of G. So symmetric just means that every element in X, it also contains the inverse under G. And small just means that you can't take finite union of translations of X to cover G entirely. And X is very important because what it just tells us is all the graded components outside of X is going to be semi-simple. And another data is the Z community group, and this will tell us about what we call the free realization. So these are going to be transparent objects in our category. So in the semi-simple, the modular fusion category setting, another way to describe the modularity condition is that the Muir center is maximally trivial, so it's equivalent to vect. So in that case, we only have one transparent object, which is the Manoa unit. But in this case, this free realization will take over the mirror center description. And so let me give you a trivial example of a relative modular category. So all modular fusion categories are in fact relative modular categories. So here we know that this is a linear ribbon category. The M trace, I can choose it as the categorical trace. Now it's semi-simple, so everything is projective. And so I can define the categorical trace on the idea of projectives, which is the entire category. And this is a completely valid choice of a non-zero M trace. And then for the relative data, I can let G be the trivial group. So I can view it as an ungraded category. This small symmetric subset, which tells us about non-semi-simple sectors, I can let it be the empty set. And the free realization part will just be the trivial group as well. So in this context, this free realization is precisely the monodal unit. And this tells us that the mirror center is precisely vect. Okay, so next I'd like to tell you guys about a non-trivial example. So let's just recall what we call the unrolled quantum SL2. So just think of this as an algebra where Q is a 2R root of unity, so it's an even root of unity. So here are the generators and relations. So if you're familiar with the representation theory of quantum groups, this is just the usual SL2 relations on the top, on the first line. And then we have this extra generator H, which acts like the logarithm of K. And then the bar on the top of U will just mean that e to the r, f to the r equals to 0, where r is once again, we're taking the 2r root of unity for Q. Okay, so when I say we have a weight module, so take a weight vector with weight lambda. What it means is that we're going to keep track of two things. One is that kv will be q to the lambda, and hv will be lambda v. So by weight we mean that we're going to keep track of q to the lambda and lambda. And for categorical reasons, this will preserve the ribbon structure. And so an example of a relative modular category is the category of finite dimensional weight modules over this unrolled quantum SL2 at an even root of unity. So the modified trace, the M trace that I can choose will be the modified trace that I defined earlier that involves the partial trace. And this will be defined on just the projectives, so not the entire category. And in this context, the relative data will be G will be the complex numbers mod 2. The small symmetric subset will be Z mod 2Z, and the free realization part will be Z. So I'll talk more about this in 2 slides later. So let's kind of talk about how this categorical structure differs from the usual semi-simple context. So for the rest of this talk, let's focus on the 8th root of unity. So when R is 4. So first, like I mentioned many times, there are infinitely many isomorphs in the class of simple objects. So here's the classification of simples for this particular category. We have Sn, tensor, the free realization part. So n can be 0, 1, or 2. And then the free realization can be any integer. And then what's more interesting are these new simple projective objects, these V alphas. So for every alpha in this set, we have a simple projective object. This is 4-dimensional because R is 4. And if you compute the usual quantum dimension, this will be 0. And so we're going to endow it with the modified quantum dimension, which is a non-zero scalar. Another feature that is different is, of course, non-semi-simplicity. So as a concrete example, if you take V0, so 0 is in this set. If you take V0, which is a simple, you tensor it with S1, which is a non-projective simple, you will get this projective indecomposable module that is a projective cover of S2, and S2 sits right inside of it. So here's a weight structure, and you could visually see S2 sitting inside of it non-trivially. So there's infinitely many isomorphic classes of simple objects, and it's non-semi-simple. And maybe when you first kind of approach the subject, I hope that no one is freaking out that there are infinitely many simples and it's non-semi-simple. And so I think it's worth addressing that um, it is not that bad. So here, let's go back to the relative data. So here,
Can you go back? Can you go back the
yes,
slide?
this slide here.
Yeah. So if you take 3 in the standard semi-simple case, that's the one you're quoting on. That's 4 dimension.
Yeah, so
Is it we
S3,
alpha just some kind of a deformation of that guy?
so S3 is V0 here.
Or it's V0. So everything is just a
Yes.
deformation of that guy, the V0.
Yeah, so V0 generates the projective ideal. So
And they are
the way
all
they
4 dimensional.
so yes, so all the projective simples will be four-dimensional. Yes.
Okay, so all the way alpha 4 dimensional as a representation.
Hmm.
Okay, okay. So it's just some version of that guy.
Hmm. And these are non-projectives. So these are projective simples. And
Yeah,
here's a
so they're all
not
scalable. Okay,
simple projective. Yeah.
okay. Thanks.
So I want to address something about the finite, the infiniteness and the non-semi-simplicity. So here's the relative data. So let me just unpack each G, X, and Z once again. So G is the complex numbers mod 2 additive group. So what this means is that our category is graded by complex numbers mod 2. That's all that means. The way we're bucketing our objects is by if V is a highest weight G mod 2, then it will live in that G graded component. Now, X is the important guy here. So X will tell us that if we are outside the zero and first graded sector, then it is semi-simple. So everything outside of these two graded components are just semi-simple objects. And only in the integral weights, we will have non-semi-simplicity going on. And another thing that I should mention is that if you just forget the free realization, so up to the free realization, each graded component has only finitely many isomorphism classes of simples. So the way I visualize this category is this complex numbers mod 2 strip. So if you view this as a playground, as long as you're avoiding the 0, 1 potholes, then what you're doing is you're playing the exact same semi-simple game as you did in the semi-simple setting. And so despite the fact that the category as a whole is non-semi-simple and there's infinitely many isomorphism classes simple objects, these categorical structures are nice enough where you could play semi-simple games and have enough finiteness conditions to play the same exact games as you did in the semi-simple setting. Okay, so now I'll kind of dive into more of the quantum
Yeah, no,
computation.
there's a question here.
Mhm.
Do you know the grain ring, which means you know the fusion of everything and all the relations?
Do
You
I
know the
know
notion
the
of a
fusion
grain
ring?
ring, right? It's not Grothendieck, it's the one which has everything.
So you're asking if I know the entire fusion rules of the entire category.
Yeah, the entire
So okay,
complete presentation of the category.
so if you're talking okay in the generic sector, so outside of 0 and 1, we know everything. Inside 0 and 1, we know all the simples and the projectives, but there are monsters in 0 and 1. There will be these non-projective, indecomposable guys that will look very weird.
Yeah,
But
that's
so
that.
I don't know the
Okay.
entire fusion rules in the 0 and 1 graded sector.
Okay, that's not surprising because that's normally very difficult to get, which is the
Yeah.
full fusion grain ring of the thing.
And my understanding is that there is like maybe like a weight, so kind of like how this is a weight space structure, there's some weird tower of weight space structures that you can generate. And so personally, I don't know what the fusion rules are within the 0 and 1 graded component, the singular sectors where we have non-semi-simplicity going on.
I would be surprised it's known, but
Yeah.
it's an interesting question.
Hmm. Yeah, so let's get into the quantum information portion. So before I do that, let me first tell you guys why we thought that this was a good idea to even begin with. So from the quantum topology perspective, these non-semi-simple TQFTs have advantages over the traditional semi-simple TQFTs. So just to highlight a few, in particular, we have examples of pairs of length spaces that the standard Reshtikin-Tarayev theory cannot distinguish, but these BCGP TQFTs are able to distinguish at the level of the three manifolds. Another feature is that the mapping class group representations, we have Dane twist of infinite order, whereas in the standard Reshtikin-Tarayev theory, we only have finite order. And so maybe more interesting mapping class group representations suggest that there will be interesting braving gates in the context of quantum information. And of course, we have more simple objects. More simple objects means more hump spaces, and more hump spaces means we could find new places to encode our qubits. And so really the slogan is that maybe effective TQFT should provide effective models for topological quantum computation. And so really this program that we call non-semisimple topological quantum computation is trying to study the mathematics of the subject from the lens of non-semisimple quantum topology. Okay, so just like many things in life, with advantages, there could be some new challenges and hurdles. So the main challenge that was brought up earlier in discussion is this unitarity. So just as a review, so a unitary matrix means U dagger U is equal to the identity matrix. Indefinite unitary means U dagger times this diagonal signature matrix times U is equal to that same signature matrix. So we say that this has signature plus plus, and we say that this has signature plus and minus. So earlier I mentioned about these relative Hermitian modular categories, and this gives us what we call a Hermitian 2 plus 1 TQFT. So on the TQFT side, what it means to be a Hermitian TQFT is that the state spaces that we assign to the decorated surface are equipped with a non-degenerate Hermitian form with respect to a possibly indefinite signature. So possibly indefinite signature meaning it could be some ordering of plus and minuses. And in particular, this TQFT will induce projective representations of the mapping class group that will land in a possibly indefinite unitary matrix. So what this means for us is that the Hilbert spaces where we encode our qubits might have a Hermitian form with an indefinite signature. And in particular, the matrices corresponding to the braiding will be in the indefinite unitary matrix. And so the main challenge is really finding unitary sectors to encode our computational qubits, which I'll discuss a bit more later.
So
Mhm.
so when you have this indefinite signature,
Mhm.
do you know they always have signature zero, which means the number of plus equal the same number as minus?
So so later you will see an example where we will have a plus and minus signature. You're just asking when the
No,
plus
no, no.
is
I'm
equal to
asking if
minus.
there's a potential supersymmetry kind of thing, which is there's the same number of plus with the same number of minus.
Most of the time, or at least I guess we spend most of the time focusing on sectors where it's not the case, where there's a more dominant positive spectrum, but there probably are spaces where they're evenly balanced. But it depends on what alphas you're looking at, whether the home space will have that property or not. But like I guess on the whole category, depending on which V alphas you're looking at the home spaces for, you may have different signature. But like the one that we'll use later for the model is it has four pluses and two minuses on that home
Oh,
space.
okay, that's a little bit bad. So maybe I will, there's a, we are talking, let me say something. So I think the semi-simplification procedure, should be redone in a different way. Uh, there's all the way I understood, semi-simplification is to take a quotient. Instead, I think there's another way to do it, which is take a subspace. This is the same thing as toric code. If you write down the toric code Hamiltonian, you write down the ground state. It's four dimension. The four dimension is not a quotient like
The
homology.
subspace. Yeah,
It's
yeah.
an equivalent subspace. I think we should do semi-simplification again using equivalent subspace rather than quotient.
Hmm.
And then you can ask the question, in this more dramatic case, it is a bigger equivalent subspace with a positive inner product.
I
That would
think
be
I
the
think
first step. I highly suspicious the answer is no. Semi-simple quotient is the largest, but maybe. But then there's something I'm really interested, which is the potential of supersymmetric case. The way I want to think about now semi-simple is fermions. So even if the signature is not equal, you can still argue maybe there are different sectors. So the supersymmetry just means that there's only either even number of fermion or odd number of fermion. And maybe it can be more dramatic. There's a Mach3 structure or something. So anyway, it's just lots of speculation of how to deal
Yeah.
with this negative signature.
mhm.
Anyway, that's so it seems I know the answer cannot be supersymmetry right away. So we couldn't rule out other
You
possibilities.
could imagine the category breaking up into these different sectors for where the Helm spaces have a certain plus, positivity or negativity or zero. Like in the zero part could be supersymmetric.
Exactly. So here's something, we can easily speculate. We are mathematicians, we can speculate. So the reason supersymmetry is more or less like a superconductors. There are only two sectors, parity. And there are lots of recent theory in condensed matter talking about 4E superconductor. So that's actually get you out of supersymmetry because now I can talk about one electron, two electron, the three electron. So that's give you a more flexible gradient than even and odd. And that will also make the signature now has to be even positive or negative, can be have some structure. So it's definitely not something you can rule out completely that this whole Hermitian, non-Hermitian has to do with something like this.
Hmm.
And it's just interesting thing to
It's
consider
good to
what's
have some
possible.
ideas of any chance of any potential physical connection would be great.
For sure.
Well, that's definitely I actually firmly believe there is a connection, just a how.
Mhm. Yeah, so let me tell you guys structurally what these relative Hermitian modular categories are. So just kind of in the same format. Structurally, this means that it is a relative modular category that we discussed earlier. It is also a Hermitian ribbon category. So in short, this means that there is a dagger structure that is compatible with the underlying ribbon structure of the category. So here are some examples and how it appears. And we also require that the M trace is real. So you should just think of this as that the dagger structure is also compatible with the modified trace structure. And so in the context of our qubits, so it just means that if we take a trivalent graph, we can take a dagger and we'll just, in this context, graphically, we'll describe it as the upside down graph. And we can take the inner products of our states, which will utilize the modified trace dimension. So this is an endomorphism on a projective, and I can take a modified trace. Okay, so I need to give you guys an example of a relative Hermitian modular category. So earlier, I said an example of a relative modular category is this category of finite dimensional weight modules at the eighth root of unity over the unrolled quantum SL2. So what we'll do is we'll take the subcategory of this category generated by these set of objects. So here generated just means that I can take finite tensor products of objects in this list along with its duals and observe that rather than taking the complex numbers, we will only take the real sector. So we need to take the real sector in order to satisfy this condition here. Oh, one thing I should mention is that notice that when F is the identity on a simple, projective simple, this is just a modified quantum dimension on that projective object. And so this imposes that the modified quantum dimensions on our projectives is a real value. So here, once again, I take this subcategory generated by these objects. This is a relative Hermitian modular category. And for the rest of the talk, when I say the non-semisimple Ising anyon model, I really mean the relative Hermitian modular category that we obtain from this construction right here. Okay, so Let's just kind of look at the non-semi-simple Ising anyon model. So here are the simple objects. Here, I'm just going to ignore the free realization for now. So we have our traditional three simple objects, the vacuum, the Ising anyon, and the fermion. And based on the fact that these were originally killed by the negligible morphisms, these anyon types are now named the neglectons. And so this alpha is parameterized by the real numbers. You slash out the integers, but you're allowed 4z, but we'll just focus on real numbers that aren't integers here. So here are the fusion rules for these projective symbols. So once again, we're assuming that alpha is not an integer. If alpha is an integer, then we're in a non-semi-simple sector. So the fusion rules can be wildly different. So in the semi-simple case, V alpha tensor S1 will decompose into the direct sum of two V alphas. So alpha plus 1, alpha minus 1. And tensoring with S2 will give us alpha plus 2, alpha, and alpha minus 2. Now, what I think is more interesting about this category is when we compare and contrast between the semi-simple modular fusion category, so the Ising modular fusion category fusion rules, and this relative Hermitian modular category fusion rules. So here I wrote them side by side. So here you should take a few seconds to figure out what is different about these two fusion rules. So within a few seconds, you'll notice that there are two differences here. It is this V0 that appears in the tensor product of S1 tensor S2, and this projected cover of S2 that appears in S2 tensor S2. So notice that this is an augmentation of the semi-simple fusion rules. And in particular, the objects that we are augmenting by are precisely the ones with vanishing quantum dimension. So these are the objects that gets killed in semi-simplification. So maybe going back to what Jonghan was discussing a couple of slides ago, rather than viewing semi-simplification as a quotient, maybe we can take some subspace that ignores these factors here. So maybe that is one way that we can think about semi-simplification is by just ignoring the objects that involve zero quantum dimension.
So what is zero? Is that just with zero?
So zero is our notation for V zeros because yeah, so we like to use alpha tensor sigma, and then
Okay.
alpha can be any value in this set.
So
So
it
yeah, so
seems
when I say
all,
zero, it's
yeah,
V0.
it seems all it did is to promote the fermion into a non-binary anyon
Yeah,
by
it
adding
seems like so.
P2. So P2 is the dead guy in the semi-simple case, right? You just resurrect this one and make the fermion into a non-binary anyon.
Hmm.
Yeah.
Yes.
So P2 is the one we killed before, right? It's the
Yes, we
projector.
kill P2 and V0. So V0 is the S3. So it
V0 is
is,
that simple projective that would have been S3 if the highest weight 3. And
Well, so
P2
before
is
they are
one
the
that's,
same in the semi-simple case.
yeah.
They, they are so now they are resurrected into different things, and then this makes psi into the fermion into a non-binary anyon.
mhm. Yeah,
And now
so
we have an
so
issue about unitarity.
but it's not clear to me what P2 means physically because I feel like when I first learned this subject, it's like each anyon type represents an isomorphism class of simple object, but this is not a simple object anymore. So now it's not entirely clear to me what P2 means with that formalism.
Well, I think it's very easy to imagine what this would be. So if you think about the big theorem, I think it's called Swan-Serre theorem. So a projective module is a bundle. All it means is that the anyon before missing some extra structure. So P2 is just a bundle over another thing. So that's the canonical algebra. A projective module is just a module of a bundle versus a vector space, vector bundle. So I would just interpreted P2, whatever this V alpha R is the original non-semi-simple with extra structure.
Hmm.
And
Yes. So
then
his
there's an issue about
endomorphisms,
compatibility of symmetry.
his endomorphism space is two-dimensional also. So that's kind of one of the things that's interesting about that guy.
I think that's actually exactly what I was thinking about the direction to go, which is the vacuum shouldn't be just harm is one dimension. The vacuum has extra structure, and the structure has to do with symmetry. So, just standard in supersymmetry, the vacuum can be infinitely dimensional, and that's give these new things. So
Hmm.
anyway, I don't have anything concrete to say, but I just think there are lots of room here to make sense of it.
Yeah, I think it would be also interesting if someone were to study like replacing all these SNs with their projective covers because their projective covers will have all the information of the SNs. And so it'll be interesting to study like P1 tensor P1 and study what that might look like. But that is just a side comment. Um, yeah, so once again, just like the semi-simple story, we computed our trivalent matrices. You can compute the F symbols, R symbols, they satisfy the pentagon, hexagon axioms, etc. And using the Hermitian structure from the relative Hermitian modular category, you can compute these B symbols that involve the dagger. And so you use these B symbols to normalize your braid matrices. And so now let's talk about the qubits. So the way we encode our one qubit is in the Hom space from V alpha to V alpha tensor S1. So there is one neglecton and two Ising anyons, and they'll fuse into a single neglecton. And so when alpha is a real number that's not an integer, so this is a semi-simple decomposition. And so this Hom space is two-dimensional. Here are my two basis elements. I'll label them one as 0 and the other one as 1. And if I take the inner product of my basis elements, here this graph tells me the signature. And so notice, so I should mention that this is the what this graph is showing is the signature on the 0 and the signature on 1, and then taking the sum of it. So when alpha is in the open interval 0 and 1, one of them will have a positive signature, the other one will have a negative signature. And same goes for the open interval 3 to 4. So these are indefinite unitary sectors when alpha is in these two ranges.
This goes back to Zheng Han's comments earlier. So like these two ranges are the part where you could potentially like look for some kind of supersymmetry, and then there's the plus plus space sector and the minus minus sector down below.
Yeah,
Mhm.
actually, this is a perfect case. So first, I assume this category has some duality. Could you rewrite the Hom space as V alpha cross S tensor S1 to V alpha tensor S1? It's just the same Hom space between itself.
Yes.
Well, then that seems to be obvious to say that S1 has a super partner because now the Hom space between itself is two-dimensional.
Right.
Mhm.
I'm just saying, now S1, we're just saying that S1 actually has, a odd part. And the Hom space now is the even C plus all C.
Mhm.
So, and then this is almost like a true, supersymmetric setup.
Yeah, I see. So like now instead of just having like a bunch of S1s, you just stick a V alpha on the side. That adds a supersymmetry, at
Yeah,
least in the
exactly.
case where the metric has mixed signature. I
I
don't know
think
how the
actually I
signature of the
think the right
metric
way to
plays
do
into
it
it.
is to make it imaginary tensor positive. It's positively plus I tensor in order to be algebraically consistent. But anyway, I don't think but I think what I was saying is that instead of using sigma to do quantum computation, now you're using sigma, which is S1, I believe, tensor V alpha, and use that particle.
Yeah.
And your qubit is just half space of itself rather than, some other full anyon, which
Yeah.
is perfect fine.
Yeah, that's interesting.
Yeah, anyway, I start to understand what is going on.
Mhm. Yeah, so there are when alpha is between 1 and 2, this is negative definite. And when alpha is between 2 to 3, this is positive definite. So these are two perfectly definite, honest unitary sectors that we can encode are 1 qubit. So let's just focus on alpha being the range 2 and 3. So this is a positive definite sector. For our higher order qubits, so our 2 qubit, you get by just adding 2 additional Ising anyons. For the n qubit, in totality, we have 2n number of Ising anyons. And so what I should mention is that in the range, when alpha is between 2 to 3, actually, let me first say what my computational subspace is. So in the 2 qubit Hom space, this is a 6-dimensional Hom space. So 4 of these basis elements will be reserved for the computational subspace, and the other 2 will be reserved for the non-computational subspace. So the way we define our computational subspace is when every other intermediary fusion channel is alpha. So notice that our computational subspace, the 0, 0, 1, 0, etc., the middle guy is alpha. And for the non-computational subspace, the middle guy is not alpha. So alpha plus 2, alpha minus 2. And for reasons later, this is a good choice of the computational subspace. And for the higher order n qubits, the computational subspace will be when every other, so the V1 prime, Vn minus 1 prime, they are alphas. And what it turns out is that in the range between 2 to 3, our computational subspace will be positive definite, but one thing we need to take into consideration is that the Hom space as a whole is indefinite. So in particular, for our 2 qubit encoding, 5 of these guys will have positive signature, and this first non-computational basis will have negative signature. So this is a 5-1 signature Hom space when alpha is between 2 and 3. Okay, so in terms of the braiding, one thing that I should mention is rather than using the full braid group, we use the affine braid group. So it's a subgroup of the braid group. And the reason why we do that is because we want our braid group representation to be an endomorphism of the Hom space that we encode our qubits. And so we require the alpha to be fixed like a pole. And so this is precisely the affine braid group. So rather than having generators B1 to Bn minus 1, sorry, or Bn, we will have B1 squared as the first generator. And so B1 squared will just wrap around the pole and everything else just acts like the normal braid group generator. And so on our 1 qubit space, once again, you can write out the matrices. So it'll be a diagonal matrix for B1 squared. You just collect the R symbols. And then B2 will be, you apply F, collect the R symbols, F inverse, and you'll get this matrix here. This bolded B is just some normalization factors. And what it turns out is that unlike the semi-simple case, we actually have 1 qubit density. So this B1 square and B2 will generate a dense subgroup of SU2, as long as alpha is not these two. So the reason why we're getting 1 qubit density is because this B1 square, this alpha pole braid, will now have these entries that will depend on alpha. And for number theoretic reasons, as long as alpha is not these two values, we can generate a finally generated dense subgroup of SU2. So there's a criteria for 1 qubit density, and we just can't have alpha be these two values here. Okay, so the only thing I'll mention about the 2 qubits is that there is a mixture of numerical techniques and topological techniques. So for SU2 tensor SU2 density, so we have SU2 density on the first component because the way we encoded our 2 qubits allows us to just translate that to the first component. Now to get SU2 density on the second component, you can apply what we know as the Juicy-Smurfy operator. So topologically, this diagram is equivalent to this picture here. And so notice that we leave the first component unaffected. And then the second component is precisely acts like the B1 square on the 1 qubit encoding. So you can get SU2 tensor SU2 density. And for approximating a low leakage entangling gate, we did that on a alternative basis. So we chose this basis to look for this low leakage entangling gate because when you fuse two Ising anyons, you'll either get the vacuum or the psi. And to this is a nice basis to look for a controlled gate because of this vacuum, if I were to braid this vacuum strand, it acts like the identity. But so the goal is to find a braid where I can braid this side strand that doesn't act like a diagonal phase matrix. And so by modifying Reichart's algorithm, we could approximate a low leakage entangling gate. And in particular, the strategy is essentially there is three 2x2 blocks going on. So this is the identity block. And then we'll group these two basis elements and these two basis elements together. And then the modification of Reichart's algorithm allows us to essentially exponentially suppress the off-diagonal entry so that we could achieve this low leakage into the non-computational space. And so what we discovered is that unlike the semi-simple Ising anyon model, the non-semi-simple Ising anyon model is universal for quantum computation by just braiding alone. And in particular, the qubits can be encoded in positive definite computational sectors. And that is the end of my talk. Thank you for listening.
Yeah,
Maybe
thanks.
I can make a comment quickly. So, like I find already pretty physical in the following sense. So, I think Sean's here. Many years ago, Sean and I wrote a paper on WS3. And recently, there's a new, I think, lots of work from Harvard try to use the idea of Brasco and Kitaev, which is to do the same thing using, I would call internal degree freedom, which is, well, it's kind of hard to say if you don't know the labels for WS3. So normally we compute using an anyon called D, which is a pure flux. And then there's a fusion rule says the Helm space has a particle A and a C, and we only use the fusion tree to do quantum computation. That's the standard topological quantum computation setup. But it came from Kitaev, and then I think Pascal, they try to use the C as a two-dimensional representation. So to me, it's kind of illegal because using local degree freedom. But you can argue there is some protection. So to me, this whole setup you are talking about is nothing kind of similar to what we have there, which is you take the sigma particle and then you attach a four-dimensional degree freedom V alpha, and your computation can be completely formulated as using sigma tensor V alpha, which is a four-dimensional representation. And then you can just quickly by saying, yeah, this four-dimensional representation, some extra degree freedom, and I'm just doing quantum computation using sigma with this four-dimensional degree freedom. In the worst case, this will be something not topological protected, but I don't believe so. I think there's some protection. So to me, this is as physical as the WS3 using a two-dimensional internal degree freedom. So anyway, so I think there's lots of possibility here to make it into some kind of a physical system.
Yeah, but again, I guess in the non-semi-simple setup, it's not clear exactly what what kind of objects of the category describe anyons. Are they simple objects or are they projective? Maybe
I think the
projective.
projective. Actually, I don't like simple. No, actually, I'll move on. I think a projective is more interesting. So here's the analogy. If you think about mathematical physics, there's this fundamental tension of mathematics versus physics. If you think about the most successful quantization gauge theory, the way it does it is always make it non-unitary first. And that's called BIST. And then you recover physical degree freedom using something else, the homology or something. I regard this whole thing about semi-simplification is completely the same story. We always go to non-unitary first, and then you recover what is physical. And the way to say, oh, we can semi-simplify it works, but not the only way or the optimal way. So I personally now prefer projective objects to simple objects.
One
So,
obstacle that we have to sort out, though, I agree that expanding to projectives is a good I mean that seems to be what this idea is suggesting. One area where
so
I'm nervous though is on what operations you can do on those projectives, because this category or this Hom space is indefinite unitary. There's a perfectly good braid, which is the B3 on this picture that Sung was drawing for
yeah,
2 qubits, the one that entangles the two.
yeah,
Um, if you do a B3, you're hitting the hyperbolic part of the metric. And
yes.
so if that's a physical operation, we could use that to get like post BQP computation. So like I'm starting to think now these can't actually be like physical anyons that we're braiding, because if they were, that hyperbolic metric would let us boost amplitudes and do post BQP. I started this. I just realized this very recent after we've spoken
Okay.
recently.
Okay. So
Yeah.
I think I still definitely stand on that one. Anybody get beyond BQP, I don't consider it physical. But let me say why I think it should be physical. So if you think about in general quantum field theory, what will make a theory physical and stable? So there are two obvious extremes. One is like topological thing, which you have a gap, and they are very stable. But that's not the only way. The other way is you have a semi-physical symmetry. So I believe that's where we are going to,
Mm.
which is this non-unitary, non-semi-simple thing means that we are combine the topological protection of a gap with a symmetry. But the subtlety is what symmetry you are talking about. There are two kinds of symmetries. One is kind of global, like topological. Another is kind of like local symmetry. If you take gauge theory,
Local
this is
symmetry.
people talk about color symmetry versus flavor symmetry. I think the double S3 story exactly this is phenomena of topological means color and local means flavor. But for a real physical system, you are entitled to local symmetry also. So I would say your non-positive definite part could make it positive by sacrifice symmetry. The inner product won't be a topological inner product, will be a inner product symmetric under topological symmetry with a little something else.
Ah,
So that's where I don't have a proposal, but I'm starting to see the
yeah.
ingredient is pointing to
Well,
that direction.
I like your idea of just looking at the V alpha tensor S1. Like that's a simple Helm space. Like if we can
Yeah,
understand that space very.
that's exactly what you are doing. I'm pretty sure if the all the duality give me correctly, you are computing using this new particle, which is sigma attached with some other degree of freedom V alpha.
Instead of doing multiple copies of that, we just need the one four-dimensional internal degree of freedom, and then we can start tensoring with S1 like we did before. It's not
Yeah,
like we have to do V alpha tensor S1 every time.
I think you should interpret it as sigma has acquired some new four-dimensional degree of freedom.
Right.
So we want like this basis here.
No, no, normal
I think
basis is
all your
fine.
Hom space is between S1 tensor V alpha. And V alpha is a single four-dimensional space. You can just say this four-dimensional degree of freedom have a new quantum number called alpha, which is almost topological.
Yeah.
Anyway, it's all speculation, but I actually probably now more convinced than you they are physical. I mean, anyway, that's all.
Thanks, Johan.
Thank you.
Yeah. Any other questions for Sun?
Yeah, what is the algebraic data on the Hopf algebra that corresponds to this like relative modular category or the Hermitian structure? Like what does that look like on the Hopf algebra?
So the Hopf algebra that we're using is this unrolled quantum SL2.
Sure.
My understanding is, if I recall correctly, it's been kind of a while. Um, I don't think this is a quasi-triangular half algebra, but even though it is not, you could just take the naive R matrix and use it to construct the braiding on the category. So I think it lacks some
Sure.
features,
But how do you get
but
G, X, and Z and
oh, you're asking about the G, X, and Z?
yeah, what does that look like in the Hopf algebra?
So my understanding is that this G, X, and Z comes from the root lattice and the weight lattice structure of the Hopf algebra, but I don't know much details about it at the moment.
Okay, so could you do this for a general finite, or I guess you don't need finite dimensional, just
Yeah,
for a general
so
Hopf algebra?
yeah, so in fact, relative Hermitian modular categories were constructed for most finite dimensional simple quantum groups. So there's a paper by Aaron and others and Josh that does this construction. It's a 2024 paper.
In that paper I just put in the archive, we also talk about it from the Hopf algebra perspective about like what structure do you need on a Hopf algebra to get that
Oh,
relative G stuff.
oh, perfect.
Mhm.
And the Hermitian form, is that also in this paper?
Yeah,
Mhm.
yeah.
Okay, fantastic.
Sounds good. And also, if anyone wants to see the other bases for the same Helm space, here are the 14 total bases. And I guess these slides will be online, so you can just zoom in and check your answers to see if you understand the fusion rules. Mhm.
Any more questions?
Um, maybe I don't know, is my mic working now? Hopefully.
Mhm.
Yes. Okay. So how algorithmic is it to approximate a certain quantum gate in your formalism? I mean, you mentioned, I think, C naught towards the end of your talk, at least a bit. Did you think about this? Some type of compiling algorithm which um, uh, converges towards a certain gate?
So this question, I think Filippo will be an expert at answering this question. So at the end, we approximate a controlled gate. So as long as the two by two block is not a diagonal phase gate, it is completely fine. So we're not really concerned about what the control gate really is. We just want to make sure that it is a control gate. But there is essentially some algorithm that you can punch in to suppress the leakage. But in terms of what the braid is, let me think. Yeah, you would just have to use these W and D braiding to actually construct the control gate.
For single qubit gates, you can do like Simon and Hormozy and those people where you do like you look at weaves and you can get pretty good approximations with weaves on the strand or weave braids. And then on the single qubits, you can do Solvay-Kataev to get arbitrary accuracy. And then you can combine that with whatever specific gate you're able to get for entangling to get arbitrary entangling gates. But the weaves for like a more interesting two qubit gates will probably be tricky. Or I mean they'd be long.
I mean, I guess in general, the Solovay-Kitaev algorithm also applies to multiple qubit gates, right? It's just here from the braiding, you can first of all approximate a particular two qubit entangling gate, and then use that as a building block, and then apply. I mean, in general, you can apply the Solovay-Kitaev algorithm to approximate other gate as well. But maybe there are more efficient compiling algorithms that exist. Um,
I think that's an understudied aspect of this, the efficient compiling. There's a lot of techniques known for Fibonacci case for doing it efficiently.
yeah. Um,
And can I ask another question? I mean, you talked about the affine braid group, and to me that's associated with a braided module category over some braided monoidal category, at least secretly. Is this some hidden ingredient in your theory, or is this just
The
a
braided
computation?
structure of the category?
Well, I mean, sure, you have a braided monoidal category, but by fixing that the first input of your tensor is always V alpha, right? You take a braided module, you take a module category where you say, well, it's all the tensor products of elements where the first tensorand is V alpha. So this probably is a braided module category you're looking at. Some subcategory in your big category which has all tensor words starting in V alpha. And I was just wondering whether you were thinking about this aspect, whether it plays a role, because I mean, from a mapping class group perspective, right, this also means you would think, for example, for a surface with a fixed boundary and you take the Dehn twist around the boundary, something like this. Or well, you have a torus and you have the torus loop.
Yeah, so hey, could you reiterate your question?
He's just talking about the role of module categories in the fact that we fixed the first alpha makes it this is a natural module category. I don't know that we were especially thinking about that language. The reason we used this specific version was because it was easy to encode the positive like to it behaved well under like sticking more and more. So it's just probably related inadvertently to your module category question. As we stick on S1s, we can keep the same range and have the inner product stay positive definite where we wanted it to be. That was kind of the critical piece. But I'm sure there's more structure there that we hadn't really worked out, or we weren't thinking so hard from that direction.
Yeah, maybe another comment is that uh, I think in literature this is called the annulus break group. Or another way to say is the mapping class group of the one puncture disk. But I guess here they chose this break group because they are the breaks that preserve the Helm space they're using to encode the qubits.
Mm-hmm.
Yeah, but for braided module categories, you always get solutions for the well, by definition, right? A braided module category for me means there is a solution for the reflection equation. So you get this B1 squared type braiding operation there. I was just wondering whether this is a direction which you explored, whether gives you something interesting to really work with. Well, as you said, the annular braid group, different braided module categories.
Yeah, it could be, yeah.
Okay, I'm confused about something here. I thought the alpha is mod 2. Why you don't write 0, 1 instead of 2, 3?
Sorry, say that one more time.
Your range of alpha, I thought that thing should be mod 2. So
So
should be
there will
0,
be
1 instead of 2, 3.
so the feature of this interval will be periodic mod 4.
Mod 4.
It would be periodic mod 4, and the reason why is because of the free realization. So really what the free realization is this one-dimensional transparent object that bumps up your weight by 4. And so you will see symmetries happening every mod 4. But this 4 is coming from the eighth root of unity.
Yeah, but I'm also confused. I thought before you have a C mod 2Z at
Yeah, you mod 2z. I don't know.
Oh, okay. So for the relative modular category, alpha is C mod. So alpha is in this set. The grading on the category is C mod 2Z.
Oh, I see.
And
Okay.
then
Different.
in the relative Hermitian modular category setting, alpha is going to be only the real sector, and the category will be graded by the real mod 2.
Okay, I think maybe here you mean here alpha is not a grading sector, right?
Alpha is not a grading sector.
It's not grading
The,
sector.
the
Yeah.
grading is mod 2, but the choice of alpha is going to be in the set. Yeah, so there's a difference between the grading and the
Okay.
alpha choice. Yeah, so sorry. So this is not mod 2 is this is for
Okay.
each choice of alpha, we have a genuine simple object.
Okay, so I guess that's it. Thanks a lot, San, for giving such a clear talk.
Thank
Also,
you so much for the invitation.
yeah, special thanks to Junghan and Aaron for contributing interesting discussions.
Mhm.
All right, I'll see you sometime later.
Thank you so
Bye.
much.
Yep. Bye.
Bye.